In this worksheet, we're going to be practicing ranking substances based on their acidity using qualitative methods. Qualitative means non-mathematical or non-numerical. So this means that we're going to be ranking substances using ARIO and not using Ka values or pKa values, which would be quantitative or numerical. So we're just going to start by reminding ourselves what the letters represent in ARIO. A stands for the atom with the formal charge. R stands for resonance, the more the better. I stands for induction. And O stands for orbital hybridization. And on this particular worksheet, I'm not going to be going over exactly what is meant by each one of these different criteria. If you're not familiar with what this represents, then just go backwards a couple of videos where I explain it in detail. In this video, we're going to be actually applying ARIO. Also, another thing that we want to be thinking about before we jump into the two examples that I have here, we want to remember from general chemistry the relationship between the strength of an acid and the strength of its conjugate base, not just any random conjugate base, but the relationship between the strength of an acid and a conjugate base. In Gen Chem, you learned, but maybe you have forgotten, that a strong acid produces a weak conjugate base and a weak acid produces a strong conjugate base. There's this inverse relationship. The stronger the acid is, the weaker the base is, and the weaker the acid is, the stronger the base is, and that relationship works in the other direction as well. So if you have a strong base, it produces a weak conjugate acid. If you have a weak base, it produces a strong conjugate acid. Again, there's always this inverse relationship. So the first actual example that we're going to work on, we've got 3 different substances. We're being told that they are all acids, and our goal is to rank each one of the acids according to its different stability/reactivity. This is something that a lot of students struggle with the terminology on this initially. If something is stable, that means that it is reactive. And if something is unstable, nope, see, I messed that up too. If something is stable, that means that it is not reactive. And if something is unstable, that means that it is reactive. And then when we bring the strong versus weak designations into that, something that is weak is also something that is stable and unreactive. Something that is strong is unstable and reactive. So when we're ranking the acids, it actually is a lot easier for us to think about them in terms of their conjugate bases first and rank the conjugate bases. And I'll talk about that once we get into it. So what we want to do is draw the structure of the conjugate base of each one of these substances. The conjugate base is going to come from each one of these acids losing or donating an H+ ion. So for each one of these substances, for each one of the acids, we want to get rid of the hydrogen, and we also want to get rid of the positive formal charge. For the first guy, H3O+, it's just going to lose a hydrogen atom. The electrons from the oxygen-hydrogen bond are going to move onto the oxygen atom as a lone pair. That just makes water. This guy over here is a little bit easier to do next. We'll do that one next. When this guy reacts as an acid, it's going to get rid of one of its hydrogen atoms. It could be any one of these hydrogen atoms. They're all the same. It's going to get rid of a hydrogen atom, and the electrons in the carbon-hydrogen bond are going to move onto the carbon atom as a lone pair, which is going to look like this. And there's going to be a negative formal charge on that carbon. This one's a little bit trickier because there are hydrogen atoms in 3 different spots on this molecule, and they're not all the same like they were in this example. So we would have to know which hydrogen atom to choose to remove in this molecule. And honestly, for this particular problem, it doesn't really matter which hydrogen you choose. You're going to come to the same conclusion anyways. But the hydrogens in the center here, these are what we refer to as the most acidic hydrogen. That just means that they are the ones that are easiest to remove from this molecule. And when that hydrogen is pulled off, it's going to leave a lone pair of electrons on the carbon and a negative charge. So as I said, in a lot of cases, it's easier if we're trying to rank the stability of acids, it's easier for us to think about this in terms of the structure of the conjugate base instead of just looking directly at the acids. And the reason for that is that the conjugate bases tend to have formal charges on them, negative formal charges on them, which makes it a lot easier for us to apply the ARIO rules. In this particular case, I did throw in an example where the conjugate base doesn't have a charge, but this is definitely not normal. In most instances, your conjugate bases are going to have formal charges, and that makes the ARIO rule really easy. It would be really difficult to apply ARIO to this example right here. So remember that we want to apply ARIO in order, which means the first thing that we want to do is look at which atom has the negative formal charge. And it's right here, and it's right here, and none of these atoms have negative formal charges, and that's the ultimate winner. Obviously, if every atom has a formal charge of 0, that molecule is super happy. It's super stable, which means that it's weak and unreactive. This guy right here is our most stable. And so now we just have to rank these two. Still, we're working on ARIO. We're still on letter A, looking at which atom has the negative formal charge. This is a carbon versus a carbon, which means that it's a tie. And when it's a tie, or when we can't use that letter to help us figure it out, we move on to the next letter in ARIO, which is R, which stands for resonance. We are looking for resonance structures. The more, the better. This molecule right here has a lot of good resonance structures. We can take this lone pair of electrons and delocalize it to make a carbon-carbon double bond, as long as we move these electrons out of the way and put a negative formal charge on the oxygen atom. We could also do that in the other direction. So lots of good resonance for this guy. This guy over here, not so much. Really, the only thing that we could do is delocalize the electrons that are in the double bond. We could move them this way, which would put another negative charge on a carbon atom, which isn't great. We could move them this way, which would just make this formal charge even bigger, which is really not good. So this molecule, even though there is resonance, there isn't any good resonance. So I'm going to say that this is our next most stable, and this is the worst structure out of all of them. Then what we're going to do is take the rankings of these bases, and we're going to relate them back to the stability of the acids using our GenChem concept. If the conjugate base is strong, that means that the acid was weak. So if the conjugate base was strong, the acid is going to be weak. Basically, all we're doing here is just reversing the rankings. That's literally all that we're doing. Now, in most instances, we're not going to be given a set of molecules and asked to rank them in order of which one is the most or least acidic. In most instances, when we're applying ARIO, it's going to be to an actual chemical reaction, and we're going to use ARIO to help us predict the direction of the reaction, meaning that just because I have this reaction written down right here, that doesn't necessarily mean that it proceeds from left to right. Notice these equilibrium arrows. Maybe it actually moves from right to left. This is important for us to understand as organic chemists. Just because we write something down on paper doesn't mean that it's actually going to work. So here is an example of how we could use ARIO to help us predict the direction of this reaction. The first thing that we want to do is identify the two acids in the reaction. There's going to be one acid on the left and one acid on the right. This is just regular acid-base chemistry. In regular acid-base chemistry, you have an acid reacting with a base to produce a conjugate acid and a conjugate base. It's impossible to have an acid reacting with an acid or a base reacting with a base. It just never works that way. So looking at these two, we have to decide which one of these is the acid, and then of these two, which one of these is the acid. So you learned in Gen Chem that an acid is something that is an H+ donor, and in Gen Chem we learned things like find a molecule and follow it through the reaction and just analyze what happened to that molecule. Pair it up with something on the right-hand side, and then just kind of take a look at what happened. And that is a very reliable trick. Another thing that you can do to help you make predictions about which is an acid and which is a base is use formal charges. Substances that have positive formal charges are generally the acids, and things that have negative formal charges are the bases. So that makes this a really fast way for us to to make these, classify these as acids or bases. So an acid is either going to be, I wrote that wrong, acid is either going to be positive or sometimes they are neutral, and a base is either going to be negative or neutral. So this trick isn't really going to help us out much on the right-hand side because everything over there is neutral. We don't have any charges to really help us, but we can use that tool that we used in Gen Chem, following substances through the reaction. If it started as an acid, that means that it turned into a base. Follow this guy through the reaction. If it started as a base, that means it turned into an acid. When we are, once we've got everything classified, then we need to focus on just the acids. So that means we're going to be looking at just these two guys right here. Now, I do want to say to you that it also would work if you focused on just the bases. That would work fine as well. Whatever you choose to do, you want to be either looking at both of the acids or looking at both of the bases. You don't want to be comparing a base to an acid. That wouldn't make a lot of sense. So we're going to use ARIO to predict the stability of these two acids. And the reason that I'm choosing to do this specifically with the acids is because in our first example, we used ARIO to rank the stability of bases, which is really intuitive. Comparing the stability of acids is a little bit trickier. So we're going to start with the letter A, which is asking us to make predictions about which atom has the formal charge. The molecule on the left-hand side has an O+, which isn't great. The molecule on the right-hand side has no atoms with formal charges at all, which means that this is the happier of the two acids. And so I'm going to begin by writing that this is the acid that is stable, and this is the acid that is unstable. Now let's just pretend that we chose to focus on the bases instead, and what would we do in that situation? Starting with A for atom with the formal charge, this guy over here has no atoms with formal charges, which means that it is the most stable, and the other is unstable. Now the problem specifically wanted us to use the words strong and weak, so where's our refresher over here? Weak is the thing that is stable. Strong is the thing that is unstable. So weak is stable and strong is unstable. In Gen Chem, you learned that strong acids or strong bases were the ones that moved from left to right, whereas weak acids and weak bases, not so much. They existed in equilibrium. In general, reactions move towards the most stable or the least reactive compounds. They move away from the unstable compounds. And so in this case, our reaction is going to be moving towards the stable compounds, which means from the left side to the right side, away from the unstable compounds. And this, even without the ARIO, should be a pretty logical thing when you think about it. We're taking two charged substances, putting them together to make uncharged, stable, neutral molecules. So it's really logical that the reaction would proceed in that particular direction. It would be really difficult to motivate these happy molecules to turn themselves into cranky, unhappy molecules. So this idea that the reaction proceeds from left to right is supported not only by these predictions that we made, but also just sort of by our general understanding of chemistry, our chemical intuition, that these molecules over here are definitely ones that are preferred and the logical products of the reaction.